So I just wanted to do a follow-up to the last video when I talked about comparing this strategy with the formula for a polynomial as opposed to this strategy where you just write out the factors and solve for this c right here. And we got down here that c equaled -6. So then we found our 0 by setting this equal to 0 with the -6 in there, and then we saw that x equaled 3, and that was our other 0. But using this strategy, we factored that a out, and every one of these factors now are pure. Whatever we find is actually the pure 0 because there's no coefficient on the x here. It's been factored out. But when we do it this way, and say we have two of our zeros like we found here. We found one of the zeros was 3. The other one was, let me use the other color. The other one was -1/2. And we went ahead and said, okay, so then if that's the case, then, we found our zeros, but we're going to use these factors to find out what the third 0 is by setting each of the constants in the factors. We multiply each of those constants and get 9. So each of these c's, -3, +1/2, and in this case it was -6. But when we factor out that a, now we're left with an extra constant here on the outside. So when we solve for all of these being multiplied, these constants being multiplied to get our 9, we have to include this a on the outside. So what we would have is we'd have, well, let me go down here because I showed it with this minus c2. Because remember, this is our 0 in this form. Since this form is showing it as x minus c2, since we use the minus sign, whatever we find for c2 is actually the 0. So the 0 here was -1/2, so it was x minus a -1/2. And then when we distribute those negative signs, of course, then now our actual factor becomes x plus 1/2. So if we're going to use these factors, like we did over here, we used the actual factors. When we use the constants for those factors, we have to include this 2 on the outside. So now to solve for this C1 here, our equation becomes 2 times this constant here, and this constant is a -C1. We use that in here for our constant, and we use +1/2 and -3. So it's really not too much different than this one where we used down here, we used our constant c. We just figured, well, okay, if we didn't know it was -6, it was just some constant c, and we used the 1/2, we used the -3. Because each of those multiplied would give us 9. But over here, we're using the same +1/2 and the same -3, and we're saying, okay, this here we have to solve for is going to be a negative C1. Because remember, this negative sign always goes with whatever's to the right of it. This one is positive, so it's positive. This one is negative, so we have a negative 3. And then, of course, we have to include the 2. So all of these get multiplied by each other to give us 9. So then when we solve, it's 2 times 1/2, which is 1. And 1 times negative 3 is negative 3 times this negative C1. And we divide both sides then by a negative 3. So if we divide this side by a negative 3, that just gives us negative 3 over negative 3, which is just 1. And 1 times negative C1 is negative C1. And if we multiply this side by a negative 3, we get 9 divided by a negative 3. We get 9 divided by a negative 3, which just gives us, well, actually, it looks like what I did here was, I probably confused the matter by skipping a step. When you have the same thing on both sides and it's all just multiplication and division, so we have the same negative sign. We have the same negative sign on both sides. You can just cancel that negative sign out, because really I could say, you know what, I'm going to just multiply both sides by a negative 1 to get rid of that negative sign. So now negative 1 times negative 1 is just a positive 1, and positive 1 times C1 is C1. So negative 1 times this negative 1 in here is just a positive 1. And so now we have a positive 9/3. So it's the same concept. If you have the same thing on both sides of the equation, you can just cancel them. I mean, even if you had like 3x and 3x plus 2 and plus, say, 5, well, that wouldn't make sense. It would have to be, let me rephrase that. Say if we had this on both sides, you could say, you know, I can just get rid of that and I still have a true statement, 2 equals 2. So it's the same concept, and even if we had, say, a negative 1 times this negative 2, we could just say, you know, I'm still going to have a true statement if I get rid of this negative 1. I'm still going to have 2 equals 2. So whenever you have the same exact thing on either side of the equation sign, you can always just get rid of it. So that's what happened here. So let me now get rid of all of this. So now you could see what I did here was, when I had this negative sign on both sides, I could just rewrite this without it. So then I got C1 equals 9 divided by 3, and so C1 equals 3. And so that would make sense then, because that's what we found over there. We found that our x equaled 3, our 0, this was our 0, equaling 3. So, you know, introducing the two different concepts might be a little confusing, but you will have to start to understand the difference between, you know, what are we solving for? Are we solving for the 0? Are we solving for, you know, here, this is the 0. because of the formula. Over here, the 0 is not this right-hand constant here. The 0 is always whatever x is here, because that's what makes this 0. So I hope I didn't confuse the matter by introducing this other strategy. And maybe I'll do a video of just using this strategy. And I did want to do a video of using this concept with the more advanced problem where I ask you to find A and give you that hint. So hope this was helpful, and that's it. Thank you.